Alrighty, so welcome back everyone. We are going to start today with, well, reinforcement learning. We're going to jump straight in. We didn't have any homework other than a little mini project, so let's get going with a very interesting topic. We're going to scratch the surface, but I think you'll still enjoy it. At least I hope so. So here we go. What is reinforcement learning? Well, reinforcement learning is what people think of when they think of AI. It's where an agent, the program, learns how to perform a task without any kind of input from the user. So things like learning how to navigate a level of Super Mario Brothers or to uh, beat someone at the game of Go or you name it. Um, Learning how to walk in rough terrain without being told how to. So that's reinforcement learning in a nutshell. It's the part of machine learning that's um, concentrated on an autonomous agent learning to do something. Um, we're going to scratch the surface with this today, but it's a very fun surface to scratch. So what we're going to be covering today is how we can make a representation of the environment that the agent would be in and an algorithm such that the agent can learn to navigate the environment in order to maximize reward and minimize punishment. Okay, so now that I've said all that, let me actually start drawing some stuff. Alrighty, so we're going to start off with a diagram. I'm going to call this the agent, and I'm going to call another one down here the environment. Okay, and then the agent is going to take an action and then there will be some reward. So let me figure out how to do this. I'm going to put a dashed line here. Okay. And I'm going to do dash dash dot 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 solid over. Okay. This is going to be the reward. And we need one more piece. We need from the environment the state of the environment. Okay. Alrighty. So we are going to be using this kind of model in order to teach our agent to do something. In our case, it's going to be to first navigate a one-dimensional maze, if you will, where there's fire at one end and a reward at the other. And the other one is going to be to navigate a two-dimensional maze, which is a little more complicated, but same basic thing. So what's going to happen? Well, the agent is the entity that's going to be navigating in the environment. And the agent's goal, the whole goal of the agent is to max the reward and minimize the punishment. Typically, I mean, I don't know why you would go the other way, but I guess you could. Alrighty. So I'm going to use the analogy of the agent is Pac-Man. Hopefully everyone has played Pac-Man, the video game, at some point. With the ghosts and the little waka 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 cheese wheel with. Never mind. So the agent in the game of Pac-Man would be Pac-Man himself. And so what is he trying to do? He's trying to max his reward. So he's going to eat the dots and the fruits, and he's trying to minimize the punishment. And that's to avoid being eaten by the ghost. Okay? So that's what the agent, how I would define that. The environment is the world in which the agent operates. So the environment contains a set of rules that tell the agent what moves are possible. So in Pac-Man, the environment is just the game grid. It is the maze and everything that's inside of it. So the ghosts, the dots, the Pac-Man himself, everything, that is the environment for Pac-Man. Alrighty? Now, what about the actions? Well, the actions are all the possible moves inside the environment that can be made. So in Pac-Man, we have 5, and by the way, I should probably update this. This is so it has a little maze and dots and ghosts and Pac-Man. Alrighty. Now, what are the actions that can be taken by the agent within the environment? Well, in Pac-Man, we got 5 actions that can be taken. You can do nothing, or you can go up, right, down, or left. Okay? So those are all the actions that Pac-Man can do. Now, let's talk about the state. We'll save the reward for last. So what the state is, it's the state of the environment. Okay? The environment sends a snapshot to the agent. So the state is what's used by the agent to determine the action within the environment. So if I'm talking about the state inside of Pac-Man, it is the location at an instant in time of of everything inside the environment. So the state, this is the location of all objects at a single instant. It is literally like you take a screenshot of the screen. That's the state. Okay? Now, the reward. The reward is the feedback that the agent receives from the environment after performing an action. Okay? So, this reward is any outcome that occurs due to an action within the environment. It can be positive, it can be negative. It doesn't matter. All that matters is that this is the outcome. When I say it doesn't matter, of course it matters, but outcome, not output. That would be, I'm in other place mode, outcome. So the agent performs an action in the environment. What happens? What does he get out of it? Well, if the reward is a dot, you've moved Pac-Man in the direction of an empty dot, you get 10 points. If you move the agent to where it meets up with a ghost, the reward is death for the Pac-Man. So the reward is used kind of loosely to encompass all possible outcomes. We tend to think of reward as being something positive and then punishment is something negative, but in the most general sense, reward is just the outcome. All right, that's all I'll say about that. Alrighty, so now that we've got this whole system rather defined, um, let's talk about what is needed within this system. Um, so first thing you need is a policy. So the policy determines what actions are taken. Okay? The policy maps from the state to the action. So I have a state that I'm given. I consult my policy, and then I take an action. Okay? So the policy can be extremely simple. It can be extremely complicated. Extremely simple might be look around yourself, left, right, up, and down. Pick the thing that offers the greatest reward in all of those directions. So if there's a dot on the left and nothing on the other three directions, then eat the dot. Um, but it could be a much more complicated policy, maybe one that looks at the placement of the ghosts on the board in relation to the Pac-Man. If 3 out of 4 ghosts are in the same quadrant as Pac-Man, Pac-Man starts heading towards one of the tunnels. So the policy is what sets the action. And what we're going to be looking at is a mathematical formula that can set the policy. Okay? So now that we've talked about that, we can move into the last little piece of this puzzle, and that is the value. Okay? So this is the reward that the agent receives I can spell, from taking an action. Okay? So the value is positive or negative or really positive versus slightly positive, things like that. In the case of Pac-Man, maybe it's 10 points for eating a dot, or um, 0 or a negative 10,000 for eating a ghost. That's not blue. Alrighty, so this value is what we're going to be using to determine whether or not a particular action is appropriate based on our policy. Okay? So you could kind of say the policy has to evaluate the values, evaluate the values. uh, sorry, just already, I said evaluate, that automatically assumed that it's considering the value. We'll just move past that. So one of the things that is a little bit tricky about the value is that in order to have a good policy, you need some complexity with your value. You need to give some value to immediate rewards. So immediate rewards, immediate, things that would occur instantly based on the state. Whatever action you take, it will immediately gain a reward versus future rewards. Okay? So I don't want to eat the dot that is immediately to my left if there's a ghost right behind it. It'll kill me right after I eat the dot. So what you want is to have some balance between the immediate, absolutely guaranteed reward versus a potential future reward. Perhaps if you have a dot and a ghost immediately behind it, you move in the other direction because you don't want to get eaten, even though that dot is an immediate, uh, has immediate positive value. Um, so this future reward is where the policies start to get complicated, because you need to have some sort of method of evaluating whether or not a given action would generate a future reward, which is where it gets complicated because the future is not set yet. So what we're going to be doing is a very simple future reward by looking at the one move ahead only, not 2, 3, or 4, just a single move ahead. All right, so this right here is the cornerstone of reinforcement learning. it gets way more complicated than this, and each one of these pieces gets more complicated. But for right now, that's where we're going to start with. Is this is our general model that we're going to use for reinforcement learning. Okay, so I'm going to clear this, and we will move on into the next piece of information. So here we go. Okay, so what we're trying to do is strike that balance between immediate and future rewards. And so this is governed by something called the exploration versus exploitation trade-off. Okay? So the exploration is focused on learning the environment. My cats are going crazy in the background if you hear galloping. Learning the environment. Okay? Exploitation is focused on maximizing reward. So, as an example, we're going to get away from Pac-Man now because I can't really talk about this using Pac-Man anymore. So let's say that we have a 4x4 grid. Okay, and I put different point values on individual grid squares. So maybe we'll start the agent down here. We'll call this plus 10, plus 10, plus 10. And then up here we'll have plus 1,000. And then right here, negative 1,000 and negative 1,000. Okay? So we're going to assume that these rewards and punishments are permanent. They don't disappear if the agent moves over them. And so what's going to happen if we set exploitation too high? What will the agent do? Too high. Well, the exploitation is all about maximizing reward. It doesn't care about learning the environment. So what is it going to do? It's going to go to the plus 10, then 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 go to the plus 10, over and over and over and over for infinity, because it doesn't care about exploring. It sees that, hey, I'm racking up score right here. This is great. Okay, now what if we have exploration too high? Now that I've made an absolute mess of this. What's going to happen? Well, it's going to ignore the immediate rewards. Instead of going to this plus 10, this plus 10, this plus 10, and then heading up to the reward, it's going to go straight there. It'll go that way. That's the correct path. Okay? It just missed out on 20 points. That doesn't seem like a big deal here, but in some cases, not maximizing your current rewards is a very poor strategy. I can think of, if you're playing, I'm a video game person, so I think in terms of video games for this. Sorry. Um, if you're playing Pac-Man, it's a good thing to eat all of the dots as you come up on them, unless the ghosts are nearby. You don't just go straight for trying to map to the ends of the maze. You want to be able to balance eating the dots and exploring the full maze. So you have to have a balance between exploitation and exploration. Okay, so here's how we're going to set that in our system. Buckle up, here we go. This is where math kicks in, so we're going to do it up righteous. This is the Bellman equation. Bellman equation. Mr. Richard Bellman came up with this in, I believe it was the 50s, and which is crazy to even think about that there were no computers that were in use at that point. Like, were there even in existence? I don't even think there were any in existence, unless you count the mechanical ones. But he came up with this to describe an autonomous agent moving through an environment when there was no way to even make that a reality. So it was purely an abstract. It was purely an abstraction, and it is totally awesome. Take my hat off to this person for coming up with this. So I'm going to write the equation out first, and then we're going to go through every single piece in excruciating detail because his equation is the foundation for what we're going to be doing today. It's actually the foundation for a good chunk of RL. Okay, so here we go. Q of S and A equals Q of S and A plus alpha times R of S and A plus gamma times the max of Q prime S prime A prime minus Q, on a bracket that, minus Q of S and A bracket. Okay? So, what do we have going on here? All right, first things first. This equation is going to be used to develop a Q table. A Q table is a numerical representation of the probabilities that will yield the maximum reward, minimum punishment. So we're going to build a table that will tell us what actions to take inside of our environment in order to maximize reward. So that's where we're heading towards. What is this? This is the Q value, and you're going to learn all about Q values in just a little bit. That's the Q value stored. You know what? I'm going to do one thing. Let me put a little thing in front of that before I move that like that. This is going to be the new Q value. Okay? The new Q value is going to get the current Q value. Okay? Alpha, just like in other machine learning algorithms, is our learning rate. I'll define all this first, and then I'll talk about what it is. R of S and A, that is the reward. Gamma is called the discount rate, or the discount. This max right here, this is the maximum future Q value. And finally, we're back to the current Q value. Alrighty. What is all this stuff? Well, the Q value, actually it's lowercase too. The Q value, it doesn't have to be, but that's generally where you see it. The Q value is the number stored for state S and action A, and this number, this value, indicates the outcomes associated with action A. A high positive Q value means if I take that action, I'm going to get a reward. A negative Q value means if I take that action, I'm going to get a punishment. So the Q value is the numeric value that represents how appealing an action is to the agent. Okay? So now let's talk about the reward. R of S and A. Okay? This is, believe it or not, the reward. The agent gets for taking action A in state S. Okay? This is the immediate reward. This is eating a dot, touching a ghost, eating a piece of fruit, whatever. This is the immediate reward. This has nothing to do with the future reward. This is strictly if I take this action, I get this reward. Okay? In the little grid that we did before, plus 10, plus 1,000, minus 1,000. Those are the type of rewards. Okay? So let's talk about this learning rate. The learning rate, I bet you can guess what that is. The learning rate is how fast the Q table is populated. Q table is populated. I don't know if I've mentioned the word table yet. So we are going to have a table of Q values, and so that's going to make our Q table. Just like with populated, there we go. Just like with the normal learning rate when we're talking about logistic regression or whatever, the learning rate is how fast you're going to try to converge to your answer. If you go too high, you may not get the proper response. Too low, it's going to take a long, long time. So we're going to stick with 0.1 just because that's the tried and true. Okay. Now the discount rate. Count, I can spell discount rate. Okay. The discount rate is how much you value future rewards. How much the agent, I should say, the agent values future rewards. Okay? So this is kind of like a percentage. When I put this percentage in, I'm saying how much I value this future reward that's going to be kicking in right here. If I do a 0.9, I place a high value on future rewards. What is that going to do? that's going to make me explore more because I want to go to where the future reward is. I want to go see what is the best possible reward that I can get because I'm going to value it highly. If I do a low value for the discount rate, maybe 10%, I don't care that much about future rewards. I'm all about maximizing immediate rewards. So in the case of the little grid we had, I put too low a value on this discount rate. This whole term doesn't amount to much. So what do I have? This reward is now king. So when it sees that plus 10, it's going to go to the plus 10, and then go to the next plus 10, backtrack, back, forth, forever. Because there's no need for it to explore because it doesn't value future rewards. It values immediate rewards. Okay? Now, this whole thing right here, this max, this is if you look one move ahead and did that action, what value would you get? This is what we're doing. We're only going to look one move into the future. So it looks at where you're currently located, the action that you're about to take, and looks at that action and sees what the maximum reward is possible for that action. So if I have the discount rate really high, that maximum value is going to weigh heavily in my decision on what to do. So this is just the maximum reward that you're going to get, the maximum value, not reward, the maximum Q value that you're going to get if you make a certain move. Okay? Now, we're subtracting off the current Q value right here. So basically, you can lump all this together and then you subtract off the current Q value because you want to see this is how much things are going to change given a specific action. By subtracting off the current Q value, I wind up getting the change only, not that is all that is going to exist for this whole thing. So what this is going to do is it's going to update the current value with the amount of change that will occur for a specific action times the learning rate. Okay? So that is the Bellman equation in a nutshell. You're going to evaluate immediate reward, potential reward, and then update your Q value based on that. Sound good? All right. So it will make more sense as we dive into a very thorough example. All right. So if you're ready, let's go ahead and jump into an example of using the Bellman equation. So here we go. Let me clear this. Actually, do I want to clear this or do I want to keep the Bellman equation up at the top? Oh, you know what? Let's keep the Bellman equation at the top. I'm just going to erase everything. I don't know if I can. No, I'll just rewrite it. All right. I'm going to pause the video, rewrite, so I don't have to waste time doing that. So here we go. Clearing it. Okay, so we're back. I have written the Bellman equation up at the top. So now let's break everything down with an example. We're going to start off. We're going to have, let's say that we have 5 states. 5 states. And each with 2 possible actions. In our case, we're going to say let A equals 0, mean go left, and A equals 1, go right. Okay? So, if it's a 0, we go left. If it's 1, we go right. Alrighty, so let me set up the states. Okay, so this is going to be state 0, state 1, state 2, state 3, and state 4. We're starting off with 0 because that's the way that Python references things. So it's a good idea to go ahead and get used to the example using it because the code is definitely going to start at 0. Alrighty. So first thing that we're going to do is we're going to have a reward table. We need to have a table that lists the possible rewards because that's going to be our environment. So this is kind of a strange reward table. Let's say that this state right here is equal to stepping in some fire. And this state over here represents finding a gem or something, a gemstone, lots of money. Okay, so what I'm going to do now is populate these states with actions where this is 0, 1, 0, 1, 0, 1, 0, 1, and 0, 1. So these are 0, I head left, 1, I head right. Okay? So if this is the bad punishment, being on the state itself heading left, which is not even possible, but we're just going to put a 0 there, and heading right is worth 0 if I started in the fire, which in the game, but that's okay, we'll just say it doesn't. And the punishment value goes in right here at S1. If I move left from state 1, I get into the fire. So this is where I'm going to put a negative 100. It's not going to have any effect if I go right from that state. Left or right, nothing here. Left, nothing. Right, there's a gem. So I'm going to do a positive 100. And then if I happen to be at the gym and was able to move, just would put a 0 and a 0 there. So this is our reward table. This is our R, big R, that we're going to be looking up right here. Okay? So that is never going to change. That is set in stone. The gym is here. The fire is here. Okay? Now let's initialize our Q table. So the Q table is going to look very, very similar. Alrighty. So we're going to initialize, this is going to be our Q table. We're going to initialize all values to start at zeros. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay? So now we're going to start at a state randomly, but in our case, let's go ahead and we're going to make this kind of arbitrary. We're going to start at state 2. So let me go make another set. This will be for the first iteration of generating our Q table. Okay, so maybe we could call this Q of, oops, I don't have enough room. T equals 1, maybe. It's the first, this is going to be the very first state that we get outside once we move for the very first time. So let's say that we start at state 2, which is going to be right here. So we're going to start here. And we are going to randomly pick whether to go left or right. And let's say that we pick to go right. Okay? So Now I need to know what to update this value with. So all the rest of them just get copied straight down. The only thing that's going to change is the value right here. And this is going to be, if I'm thinking about it, this is Q, well, I can do it right here. Q of state 2, action 1, so Q21. Okay? So let's use the Bellman equation to figure out what value gets put here. Okay, so Q of 2, 1 gets Q of 2, 1 plus, we're going to do our alpha, which is 0.1 times, if I look at what reward I get by moving right from state 2, I look up here, I see I get a reward of 0. Okay, so I'm literally looking at the reward I get in my reward table for the state and action that I'm located at, which in this case is 0. So that's going to be a 0 plus gamma, which I'm going to give a high value on future rewards of 0.9. And now I need to multiply it by the maximum value for the future move, the maximum Q value left and right for the future move. I'll look over to the future because I'm heading over to state 3. The maximum of these two values is a 0. I'll put a 0 here. And then I subtract off the value that was in Q21, and that was a 0. Okay, so I've got too many brackets here. Let me take that bracket off. All right, brush size too. So, oh no, that was correct. Shoot, I missed that second bracket right there. Yeah, that was correct. Ah, missed it. Here we go. What value gets put in here? Well, I have inside this bracket 0 plus 0.9 times 0 minus 0. So this whole thing is 0 times 0.1 is 0. So I get the value that was here plus 0, which is 0. So a whole lot of nothing. Okay. Now let's repeat the process. Except I'm no longer going to be in state 2. I'm going to start now in state 3 because that's where I just moved to when I moved right. Okay, so I'm going to be in this state and I'm going to pick randomly right or left. Let's say that I pick right. Okay, so I'll need to update this box right here, and this is Q31. Hopefully that didn't get cut off. So Q of 31. Alrighty. All the rest I copy down. Nothing changes about them. Alright. So let's run the actual Bellman equation. Q of 31, state 3, heading right, gets the value that was already stored in Q31 plus 0.1 times. Now we look up at the reward table for this location. There's a reward of 100 at that table, so I put 100 in right here. And then plus 0.9 times. Now I'll look, if I'm heading over to this set, what is the maximum Q value in these two boxes? Well, it's 0 still, so that's a 0. And then minus the value that was already stored here, which is 0. So this is going to get 100 plus 0 minus 0, which is 100. 100 times 0.1 is 10. And that 10 got added to the previous value, which is 0, so that's why it was a 10. Alrighty? So now I have this configuration. Okay? So if you will allow me, I'm going to kind of copy it above and then erase the things that are below. That way I can just jump in pretty quickly. That's the only thing that's different. And now I can erase all this. Make a pretty big eraser size too. So, all right. Erase, 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 erase. Okay. So we were here, and then we headed right, and we reached the gym. We're going to say that the game ends at reaching the gym or the fire. Okay? So my Q table, when I exit, looks like this. Everything's 0 except there is a positive 10 right here. Okay? So now let's do the next iteration. We're again going to say that we start at state 2. So let me go ahead and write that out. Box it up. Okay. So we're going to start again at state 2. And we're going to say that we randomly pick to go right again. So update this value right here. So copy down all the other values as is. They won't change. Okay. So now I'm going to update this one. And again, this is Q21. Alrighty, so I'm going to use the Bellman equation. So Q of 2, 1 equals Q of 2, 1 plus 0.1 times, what is the reward located for this location in this state in action? Well, that reward is 0. So 0. Okay. Plus 0.9 times, okay, what is the max of the Q values? Well, that maximum is 10. So now I can put a 10 here. And then I subtract off the value that I started with here, which is 0. Okay, so what do I get? Well, I get 0 plus 9 minus 0, so that's positive 9 inside, times 0.1 is 0.9, and then I added to what I had before, which is 0, so this becomes 0.9. 0.9. Okay? Now, I'm going to, I can go down just a little bit to get more room for the Bellman equation. So let's do this again. So thrilling to watch boxes being drawn, I know. Alrighty. So we are now in this state, state 3. And what do you know? We're going to randomly decide to go right. So I'm going to be looking to update this again. 0, 0, 0, 0, 0, 0.9, 0, 0, 0. Alrighty. So this is going to be again Q of 3, 1, state 3, action 1, we're heading to the right. So Q of 3, 1 is going to equal the previous value of Q31 plus 0.1 times, it looks above, the immediate reward is 100, thousand, oh, that's awesome, is 100 plus 0.9 times, it looks over to these two. What is the max value here? Well, it's still 0. And then it is going to subtract off its original value, which is 10. Okay, so what do we wind up with? 100 plus 0 minus 10, so that's going to be 90. 90 times 0.1 is 9, so this whole thing is 9. I get the previous value plus 9. So 10 plus 9 makes this 19. Okay? Whew. So far, you see how the Q table is updating? If I'm in state 3, I'm already seeing there is a very high probability that I want to head right. Left is a 0, right is a 19. 19 is way higher. I'm going to go right. If I'm in state 2, I'm already looking kind of forward. Even though the reward is 2 states removed, it's kind of trickling backwards as the Q table next to it gets updated with a positive value heading towards it. Then the entry before that also starts to update with a positive value heading to this node. So what will happen over time is this entire Q table will be populated by values that will guide the agent to head towards the maximum reward. All right, I'm going to do one last example. I'm going to change this to, let me change that to a small value so I can erase inside. A 19 and change this to 0.9. Oh, and actually I should just erase that so that there's no confusion. All right, and I'll erase this too. So this is 0.9. This is 19. Alrighty. So it reached the end, starts over. So now let me erase all this. Okay. Fun, fun, fun. Alrighty. So now let's start. Actually, you know what? Let's just do one. Let's start in state 1, which is going to be right here. And let's head left. Okay? So I'm here and I'm going to head left. So this is going to be the value that's updated. I'm just going to copy all the rest of them down. 0.9, 0, 19, 0, 0. Alrighty, so this is Q10 because it's the first state, and we're heading, the action is 0, we're heading left. So what do I get? How do I update this? Well, Q10 gets Q10 plus 0.1 times. We look above to the reward table and see that there's a negative 100 there. So negative 100 plus 0.9 times what is the previous, where we're heading, gosh, I lost my train. Where we're heading, what is the maximum Q value? Well, that is a 0. And then minus the previous value. So this is going to be negative 100 plus 0 minus 0 is negative 100 times 0.1 is negative 10. So the original value, 0 plus negative 10 is negative 10. And this is what our Q table looks like. After 3 runs, we're starting to fill things in. It will already have a blueprint on how to get to the maximum reward after just 3 runs. If it starts at state 1, it says, uh-oh, if I had left, that's a bad thing, so I'm going to head right. It hits state 2, well, that's slightly more beneficial to head right, I'll head right. Then it sees that it's very beneficial to head right, so it heads right again, and it hits the gym. So now that we have this all down, let's actually go to the code and do some runs, because those are fun. All right, so let me clear this and switch to Spider. So here we go. Okay, so here we are in the code. This is for the 1D example like we just did. So this is the environment matrix. So it is the environment and contains all of the rewards and punishments, but it's done state by state, just like we did in the previous example, where the individual actions show what the rewards and punishments are. In this case, we are going to have a fire located at state 0. If I head left from state 1, it's a negative 100. And then we're going to have a gym at state 1, 2, 3, 4, 5, 6, 7. So if I head right from state 6, I get 100. If I head left from state 7, I get to the gym. So all that's different is we've added this little tail over here because this is kind of neat what happens over on this side. Alrighty, our Q matrix is right here. We've initialized all the values to be 0. The win-loss states are going to be the states the at which we end the game. So state 0 and state 6 will end the game. All right, so the next one is get all possible next actions based on the current position. If it's the value is not none for up here, this is the environment matrix. This is where you can also set the bounds. This one says you cannot go left from state 0 and you can't go right from state 9. So, or state 9, 1, 2, 3, 4. Well, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. Okay. So all this does is it checks to see which position, what actions are next available. Um, and it returns that list. Okay. Then this one, get next state, takes your current position and an action and then feeds what the next state would be. In this case, it's really simple to do. If the action is a 0, it means we need to head left. So we take our current position and subtract 1 from it. If it's not a 0, that means it's a 1, which means we go right by adding 1 to our current position. And then is the game over? It just checks the current position, and if the current position is in the win-loss states, which we set to 0 and 6, it ends the game. Okay? These variables right here can set the discount rate, how much you value future rewards. I've got mine set pretty high at 0.9. The learning rate, 0.1. And the number of training times that I want this to go through a full set of training until it reaches an end state is 1,000. I'm going to back that off to 1. Okay? So here we go. Basically, what this is going to do is randomly choose one of the states to start in. Okay? It's going to check to see if the game is over based on the current position. If the current position is not one of the end states, it keeps looping through this. So what does it do? It gets all possible next actions, stores that in the list here, and then randomly chooses from that list. That's its action. Then the next state will be the current position plus whatever action was just decided. Then it goes into the Bellman equation. So the Q matrix sub current position and action, so state action, is the current state action plus the learning rate times the reward state and action, which is the environment matrix, plus the discount rate times the maximum of the two values for the next state. The maximum of the Q values for the next state minus the current position and actions Q value. So this is the Bellman equation just in this form. It's exactly the same as what we were using. And then after it updates that, the current position becomes the next state. So you move to the next state, just like we did in the examples. And once it loops through all the different times that it trains, it says training done, and then outputs the array that lists all of the decimal values, okay, inside the Q table. So let's run it and see what we get. But before I do that, I have to move this over, don't I? Because it won't make much sense if I don't move it. So let's see. Let's move that over here to the console where you can actually see it. So I'm going to run it once. So here, we're going to run it. And what did we get? Well, it looks like it started somewhere and then went left. And when it went left, it eventually hit the fire and then it updated the Q table with that -10 that we saw before. Okay, let's run it again. And yeah, you can still see that good. Again, it went to the left. There, eventually it'll get to the right. There it goes. Now it went to the right until it hit the gym and it updated from there. And so it'll just what happened here? It started at one of the end locations, so the game was over before it even started. And so there it went right. Ah, in this one, it actually started at one of the end positions and went left until it found the gemstone here. So that's where that 10 came from. All right, now I'm going to up the number of times that it runs to 3, and we're going to run it until we get an output that looks exactly like what we had. So let's see. Oh, that doesn't look like it. That doesn't look like it. 19. Oh, we're getting close. I saw that 0.9 in the 10. How many times is it going to take? This worked like within 5 times when I ran it myself. Oh, well, I guess we're just getting unlucky. Wow, this is crazy. It's not going to do it. Oh, well, I tried. Now, that's just running it a few times. Let's bump up the number of training examples to 10 and see what happens. Alrighty, so now you can start to see as it's populating the Q table what's going on. The first state is highly negative, -27 to the left and a 0.19 to the right. Meanwhile, if I'm in state 5 right here, it is extremely probable that I should go to the right to maximize my reward. Now, why does going left have a small positive value? It has a small positive value because if it heads left, it now has another chance to go right again and wind back up in the winning position. So it's totally fine heading left for all of these states until it hits this one, and the game is going to end if it heads left. In every other case, it can recover and head to the right till it hits the gem. Okay? So that was with 10. Now let's run it 100 times. Now we start to see what's going on. The full table. It is you can kind of think of it as kind of like an expected reward. It's not that exactly. The numbers just happen to work out that way for this. Don't jump on that one. But -86 if I had left, 20 if I had right. I'm going right. Same for this one. There's a 30-point difference to head right, 30-point difference here, a 34-point difference here, and a 40, what is that, 47 and some change point difference. So it's way more likely that I will head right to maximize my reward. Now, if I start over here, this is really cool. Look how close it is at just one away. It's within, what is that, 34? One away. And right here, it's within 37. So what's going on? Well, what it has discovered is over here, it doesn't matter if it heads left or right, it's still going to eventually bounce around until it hits the gem. So all possibilities are positive. It will eventually make it. Some of them are more positive than others, and that's the direction that will directly lead to the gem. So That's why you have this little bit over here and why I wanted to have that in there so you could see this behavior. There are no negatives over here. It's a win-win if it starts over in this location. It will eventually get to the gym and the 100 points. Okay? So that's 100. Now let's run it 10,000 times. Yeah, look at that. It's flat saying it is negative 100 if you head to the left here, and positive 100 if you head to the right from state 5 or left from state 7. So turns out that after you run your Q table uh, enough times, it converges to actual values. These values won't change if I run it 30,000 times. They're going to be almost identical. Oh, wait. Actually hit the run key would help. And there you see, the numbers are absolutely identical. So what seems to be a really a kind of an abstraction, a mathematical abstraction that couldn't possibly do a whole lot, turns out to be incredibly robust at letting an agent figure out its environment. The Bellman equation is absolutely stunning. It's one of my favorite things in all of machine learning. And it's not for machine learning, it's just used in machine learning for reinforcement learning. But it is extremely robust. Um, and it always, I've never seen it fail. So I don't think it's possible for it to fail, to be honest, at least in these simple examples. So um, there you have it. That's how you run this, and that's how you can. This is all within a one-dimensional environment. All right. So if you're ready, we're going to move from here into a 2D environment where we can actually make a maze. Because right now it's just fire in a gym or one negative punishment, one positive reward. So let's go to a 2D environment. So let me stop this and get to there. Okay, so here we are in the two-dimensional representation of the Q table. And um, although I found the code for the 2D, the 1D rather, um, and kind of altered it just a little bit. Most of it is straight out of a reinforcement learning site. I've yet to see any 2D coded. This is all I used the first one to make this one in a similar manner. So I think this is the only 2D Q table code that you can find out there. So enjoy. I had to make it myself because I couldn't find any. So here we go. Now we're going to have in a two-dimensional Q table, each of the states has 4 possible movements. I can go up, right, down, left. Okay? Up, right, down, left. And so none in our environment matrix means that that move isn't allowed. So for the first state, I can't head up and I can't head left. So that makes this a corner. The next state over, I can't head up, but if I head to the left, I have to make sure I keep all this straight because it's hard to remember what's what. Where's my piece of paper where I had that at? That's what I need is that little piece of paper. I won't misspeak with this. Where is it? Of course, I ate the paper. Oh well. Not important. I guess I can figure it out as I go. I will have to pause each time. So if I can't go up and I can't go left, that's the corner, the upper left corner. I also can't go up here, so that's the next space over. And if I head left, I get a negative 100 penalty. So this is setting the fire, if you will, in the upper left. So the upper left has the fire. Okay, I move over to the right one more state. This is a 3x3 grid. as you can see right there. So I move over one more state, and I can't head up and I can't head over to the right. So that's the right corner, but I can head down and to the left. Those are possible. Now, if I move to the next box down, this is a completely different row. If I head up, I head to the fire, right? I can head to the right, I can head down, but I can't head to the left because to the left is a wall. This is the middle one, so this is right in the middle of the 3x3 grid. I can head in all directions, everything's fine. I move to the third state on the second row, the middle row. I can head up. I can't head right because I hit the wall. I can head down. If I do that, I hit the reward, which is the plus 100, and I can head left. Now I move to the next row. I can head up, right, but I cannot head down or left, which means it's a bottom corner. Over to the next one. If I head right, I hit the gym, but I'm not able to head down. And finally, the last one, which would be the bottom right corner, I can't head right and I can't head down. Now, this is impossible to keep straight when you're just looking at this code like this. So I'm going to show you after we go through this a couple of times how you can actually draw something out that you can use to populate the environment matrix so you don't have to strain your brain too much. I can't do it without planning it out on paper. I can't just look at this and go, oh, it's obvious that this should, no, I can't do any of that. So I'll show y'all how I did it, and then you can follow suit if you want to. So let's see. So we initialized the Q matrix. They're all zeros now. So this is, again, it's a 3x3. And each one of the states holds the 4 different directions. And so the win-loss states are going to be at 0, 0, which is the upper left, and 2, 2, which is the bottom right. And the rest is pretty much identical. It's just a little more complicated because now we have to be able to update things in 2 dimensions. So, yeah, it gets a little bit weird. So we've got the discount rate, the learning rate, the number of training times, same as we did before. Let me change that back to a 9. And then here's the Bellman equation. It is exactly the same. There are no changes whatsoever to it. And then it will print out when it reaches the end, which y'all can't see. It will do a printout of the matrix, the Q table. So, and this is going to be it's hard to remember to think of it this way, but each one of the chunks represents up, right, down, left. It's going to be a series of 4 numbers, up, right, down, left. So let's train it 10 times and see what we get. So, you know what, I'm going to shift this over to where you can just see the output, and then because you'll know I'm changing some data. So let's see, we can do it just like this. So let me run this now. All right, running it just 10 times, update the Q table a little bit. So what does it see? Well, for the upper left, nothing gets updated because that is an end condition. But the next one over from it, so to the right of that one, if I head left, it's a negative 19. I can head, it doesn't list if it's not possible, it just lists the value that's stored in the Q table. I could probably change that, but that's fine. Main thing is it doesn't head left. If it goes over to the one on the right, the top row right, nothing. There's no values for it to follow. So then we go to the middle row, the left one, and it is saying you should nudge yourself to the right a little bit. It's slightly better to go right than any other direction. Then the very middle one, we should head right or down. Down looks like the best bet. It's the safest bet. Then when it gets all the way to the middle row, rightmost block, down is the sure bet. That's the way it should go to hit the reward. Okay? Then it heads, we go down to the bottom row, leftmost. There are no values there yet. But if I go over one more to the bottom middle, heading right is the smart bet. And notice it will still try to head up with a slight chance because heading up, there's still an option. Heading up would be, let's see, it'd be this one. There's still a chance that it can get back to the reward. So it's okay having a slightly positive here. So as you can already see, you're going to have to run this many, many, many more times in order to fully populate it. So let's do 1,000. Alrighty, so we've already got some pretty good values in. If I am top, center, left is a bad idea. Anything is better than going left. Right or down are much better. Okay? If I am the center row, leftmost, don't head up. Go right or down, but don't head up. So if I'm in the absolute middle, right and down are perfectly the same. And I can still head up and I can still head left and have an opportunity to recover and come back down, but it's better to go right or down. And then if I am the middle row, rightmost, heading down is the best bet, and the bottom row, middle, heading right is the best bet. So I know this is difficult to visualize first time that you do it, but if you play around with it a little bit, and I'm going to show you a way that you can kind of build your maze and actually help make sense of what it's saying with these values here in just a sec. So let me stop here and go back to the blackboard to show you how you can build your own maze. So here we go. Okay, so here we are. And let's say we want to make our maze. We don't want it just to be open like it was though, so we're gonna make some walls for it to navigate. So let's see. We're gonna start off. Let's do a 3x. You didn't see anything. Let's do a 3x3 grid and let's take our time to actually draw this out. Oh my gosh, am I unable to draw today? All right, let me try that again. There we go. We're gonna do a 3x3. Okay. And you can do this on paper or whatever. All right, good enough. Now, each one of the states has 4 possibilities. So, but I need to code them in. And so what I do, if I'm just doing the basic stuff, what I'm going to do is on each of the walls within the states, I'm going to put a value. So first off, let's say that I put my 100 here and my negative 100 here. Okay. I've got a none here because I can't go this way, and a none here. I've got this way right here is a 0 because there's a value of 0, 0, 0, 0, 0, 0, 0, and a 0 here. I move over to this one. The top should have none, 0, 0, but this one has a negative 100 value for it. So if I head left from this state, I hit the negative 100. Okay? Come over here, none, none, and then 0, 0. Right here, negative 100. If I head up from this one, 0, 0, none. And this one is 0, 0, 0, 0, 0, none, 0. I'm sorry, 100 for that one. If I head down from this node, it should be 100. And then 0, 0, none, none. And then 0, 0, 100, none, and then 0, 0, none, none. Okay? And then you just have to keep the order straight. The top one is your first value that you enter. That's the up direction. Then you move to the right. Then you go down, and then you put the left one in. So it goes clockwise from the top. That's what the values are. And if I looked at the code, I guess I could click back to that and move this over a little bit. Let's see. Go to the code here. Where is my cursor? There's the cursor. Couldn't find it. Well, you know, that's exactly what I have. Up, none. If I go to the right, 0, down 0, left, none. So that is exactly what I had. Let me go back to that. Alrighty. So that's how you do it. You start here and you go around for each of these, and that's how you code in your values for your environment table. Now, if you want to add walls, all you have to do is change what the values are. So let's say I want to add a wall. Let's see. I'm going to go with, yeah, let's go with, I'm trying to think of find a fun one to go to, a color. Purple. I like purple. All right, so let's say that I made a wall here, a wall here, a wall here, wall here, and that looks pretty good. Okay. Well, what changes? Well, I can no longer pass through here, so this becomes a 0. This, oh, sorry, 0. My goodness, I didn't say that. You didn't hear anything. Not a 0. It becomes none. So this becomes none. And this side also has to have a none there because you can't pass through that wall. Same thing here. This becomes none, none. And same thing for here. None, none, and none, none. And it is extremely easy to set up walls and everything. You can also increase the size to a 4x4 if you want. You just have to be pay very close attention to what all your states, how they line up and everything. I highly recommend you write, if you want to do the maze, draw this out on a sheet of paper and do it just like this, and then be extremely careful with how you transcribe the values, always starting from the top and going around clockwise for your list of values. Because if you miss a single value, it's going to throw your Q table off. And it is devilishly difficult to figure out what went wrong. But the cool thing about you adding walls to it is you start to see some really interesting behaviors. If I head up right here to this little like box, I'm locked in unless I head back down. Down is the only opportunity, so I should have a really high chance of heading down. And same for, you know, right here. I'm going to have I have to, in order to get to this negative, I have to start somewhere and wind my way and head left from this square. This is the only way to get to the negative reward or negative punishment. So there you have it. That is everything to do with the Q table code. I'm going to send that out, as well as a Bellman equation worksheet so you can work through a 1D example yourself if you want to. Alrighty, I hope you enjoyed it. I know I sure did. This is incredibly fun stuff, especially if you make a more complicated maze and then watch over time as it learns, as you do 100, 1,000, 10,000. It learns to navigate your maze. It's pretty cool. Alrighty, y'all have a good one. Stay safe, and I will see you later. Bye bye.